Hello, I am Quincy Brown, the General Chair for the 2020 ACM Richard Tapia Celebration of Diversity in Computing Conference. I was born and raised in the Bronx, New York, so hopefully there are some other New Yorkers here. I earned a degree in electrical engineering from North Carolina A&T State University, so shout out to the Aggies and the HBCUs. And I earned a master's degree and PhD in computer science from Drexel Engineering. So hopefully there's some Drexel Dragons out there too. I've worked in industry as a professor in the federal government and nonprofit sectors. So basically that's a long way of saying that I'm a little older than I may look. But my real purpose in introducing myself to you is to welcome you to the 2020 ACM Richard Tapia Celebration of Diversity in Computing Conference. This is the 14th Tapia Conference, and it's been 19 years since the first conference was held in October 2001. The Tapia Conference is sponsored by ACM and presented by Commanded. Though this is the 14th conference, it is our first virtual conference. When we started planning this last year, none of us had any idea of what 2020 had in store. What we knew then is that the Tapia Conference is a time when so many of us reunite with old friends and make new ones. So we invite you to stay and get as much as you can from the time that we're spending together. We are going to ask that you use social media. You can tweet, use IG, whatever else social media stuff is out there, using the hashtag Tapia2020. And you can also post to the Tapia Conference Facebook group. The demand for the conference in terms of registration this year has been phenomenal, especially considering the move to a virtual platform. And we thank all of our sponsors for their support. We appreciate the support of our platinum sponsors, Boston University, Carnegie Mellon University School of Computer Science, Cornell Computing and Information Science, Georgia Tech, JP Morgan Chase, MIT Lincoln Laboratory, Qualcomm, Stanford Engineering, the D.E. Shaw Group, 2 Sigma, UC Berkeley Electrical Engineering and Computer Sciences, University of Chicago, University of Illinois Urbana-Champaign, and the University of Michigan. Platinum government participants include Lawrence Livermore National Laboratory and the National Science Foundation. We also appreciate the support of our many gold, silver, and bronze supporters. The conference would not be possible without our supporters. So let's give them all a round of applause. All right. And I want to be sure to remind everyone that though we are virtual this year, the Tapia Conference does have a code of conduct and anti-harassment policy in place to encourage an open exchange of ideas and a respectful environment. I invite you to become familiar with this policy that is available on the Tapia Conference website. And now I'd like to invite Brianna Blazer, the chair of our Accessibility Committee, to speak with us on helping to make the conference more accessible to all of our participants. Brianna?
Thanks, Quincy. It's been a great year working on the Accessibility Committee, and every year I'm excited to come to Tapia because of the welcoming environment that we have, including for people with disabilities. So even though Tapia is online this year, it's just as important to be accessible. So remember that we have attendees with a wide spectrum of disabilities. We have folks here that use wheelchairs. We have folks that may be deaf or blind. Others may have an invisible disability, like an attention deficit, depression, or autism. You'll notice that some sessions are being live captioned. This one is right now. You can turn on the captions at the bottom of your Zoom window. It'll say captions and it'll also say subtitles. I also want to remind you that making the conference welcoming and accessible is something that we can all work together to do. So I want to offer some things you can think about doing. And remember that some of these strategies will benefit a larger group of people. So a few things to think about. If you're presenting, read and describe all of the content on your slides. If you're showing a video, you might warn the audience if it includes a lot of motion. Understand that not everyone makes eye contact when you talk to them. Other people may need more time to respond to questions. Ask at the information desk if you are having accessibility issues or need electronic versions of the presentations. As you network with people, remember to talk with diverse people this week, including people with disabilities. And if you have feedback about accessibility, please feel free to talk with me. You can find me a lot of times at the Access Computing booth, or share the information on the evaluation after the conference. So have a great conference. I encourage you to think about accessibility while you're here, and take some of what you learn about accessibility back to the rest of your life. So back to you, Quincy.
Thanks, Brianna. Now I would like to invite the chair of the Commandit Board of Directors, Stuart Feldman, Chief Scientist at Schmidt Futures and author of Make, to give a greeting on behalf of Commandit, the presenter of the Tapia Conference.
Thank you so much, Quincy. I appreciate the intro. On behalf of Commandit, the Center for the Minorities and People with Disabilities in IT, we welcome everyone to 2020 Tapia, the bigger but virtual edition. We hope you enjoy, learn, and build communities at Tapia. Commandit is dedicated to fostering innovation through inclusion. I have the honor of chairing Commandit's Board of Directors because Dr. Valerie Taylor asked me to do it, and I've never been able to say no to her. I spent most of my career in the best industrial R&D labs in computing, Bell Labs, Bellcore, IBM, Google. I'm a former president of ACM. At all of these places, I strive to improve diversity, but honestly, did not make enough progress. So I'm thoroughly committed to doing it better and bigger now. And Tapia is a big piece of that. We on the Commandit board are all committed to a more diverse and effective field of computing. You all have the opportunity not only for a personally successful career, but one that affects our diverse society in multiple positive directions. Please enjoy the conference, but also keep your eyes on the prize. I would now like to invite Gabriele Kotzis, President of ACM and Professor of Computer Science at the Johannes Kepler University in Austria, to give a greeting on behalf of ACM, the supporter of the Tapia Conference. Gabriele.
Thank you very much. It is my great honor and pleasure to welcome all of you on behalf of ACM's nearly 100,000 members from around the world to Tapia 2020. I'm convinced that no other discipline will have more impact on shaping our future than computer science and technology. This implies a major responsibility for our community, not only from a technical and scientific perspective, but also from a societal and ethical point of view. And it is important that those developments are driven by a community that values and lives diversity and inclusion. Why is it so important? Well, first of all, because differences, diversity, are the elements that make all our lives interesting. Just think about how boring our world would be if we all would be the same, act the same, look the same. That would be a terrible place to live. So we truly should value diversity, appreciate the differences, and not try to always rank differences in comparing one against the other and saying one is better than the other. We really have to overcome this kind of thinking. Second, diversity is important for our community because we build technologies, we create systems, we create computing machinery for people all over the world. And therefore it's important that also the creators come from all over the world and show the same diversity as the users of our technology. I do know from my own experience that it is very challenging to host such an event virtually, especially because the main purpose is networking, interaction. But who, if not we, as a computer community, would be able to master the technology and to use the technology to continue the discussions, even if we are not able to meet physically. I would like to thank the organizers. I would like to thank Quincy. I would like to thank all the people working behind the scene to make the Tapia 2020 conference such a great event. I'm happy to hear about the good participation because it's really an excellent venue for creating awareness for diversity and inclusion, for having an actual impact towards more diversity and inclusion, and last but not least, as the name of the conference says, to celebrate the diversity. With that, I would like to wish all of us fruitful, inspiring discussions, follow-up cooperations, and long-term effects that these conferences will have. Thank you very much and enjoy the rest of the days.
Thank you, Gabrielle. That was awesome. Now I want to welcome Valerie Taylor, Division Director of the Mathematics and Computer Science Division at Argonne National Laboratory and CEO and President of CMD-IT, to provide a brief history of the conference.
Thanks, Quincy. So I'd like to take this opportunity to tell you a little bit more about the conference namesake, that is Dr. Richard Tapia. And to do that, I'm just going to share my screen with a slide. So Richard Tapia is a mathematician and professor in the Department of Computational and Applied Mathematics at Rice University. He is internationally known for his research in interior point methods, which is used to solve linear and nonlinear convex optimization problems. He is the first Hispanic elected to the National Academy of Engineering and was presented the National Medal of Science by President Obama in 2011. Richard was born in Los Angeles to parents who separately immigrated from Mexico as young teenagers in search of educational opportunities for themselves and for future generations. He is the first in his family to attend college. Richard received his bachelor's, master's, and PhD degrees in mathematics from UCLA. And now to tell you a little bit more about Richard, something that you can't find on the website or in the program. When we were thinking about naming the conference, that is with the organizers, and this was back in 2000, we immediately thought of Richard Tapia. He's well recognized in research, as well as his outreach to underrepresented groups. When we first approached Richard, his first answer was no, and then he asked, are we aware of some knowledge about his health? Because Richard pointed out to us that many conferences are named in honor of someone who's deceased. We then went on to convey to Richard that no, we didn't think about his health, but it was Bryant York, who's in the audience today, who wrote a very sincere letter to Richard about why the conference should be named after him, given his significant work in optimization as well as outreach. After much consideration, we're happy to say that Richard agreed. Thank you, Richard. It is an honor to have the conference in your name. And that is to tell you a little bit more too about some things that we're doing here at the conference. And that is to let you know that we also have an award in Richard's name, and that's the Richard A. Tapia Achievement Award for Scientific Scholarship, Civic Science, and Diversifying Computing. In honor of the past 13 recipients of the award, our virtual rooms, networking lounge, and exhibit hall are named in honor of the past award recipients. When you join a session, there will be a slide upon entry that identifies the name of the room to honor the previous Tapia Award recipient. The room names are not given in the schedule, only the link to join is given in the schedule. So for example, we're currently in the Bryant York Auditorium in honor of Bryant York, the inaugural Tapia Award recipient. So I invite you to click on the virtual room dedication that's located in the lobby area to learn more about the past Tapia Award recipients. We also have 3 chat rooms named after 3 researchers who were very active with the Tapia conferences, but they're now deceased. So we have one room that's named after Dr. Clarence Skip Ellis, and he was the first African American to earn a PhD in computer science, and the first African American to be elected a fellow of ACM for his pioneering work in computer-supported cooperative work. Dr. Tiki Suarez Brown, she was a professor in the School of Business and Industry at Florida A&M University and a researcher in high-performance computing. Then we also have our third chat room that's named after Dr. Phoebe Lanier, who provided leadership with various programs related to increasing diversity in STEM fields. It is an honor to have the chat rooms in their names. So hope you enjoy making connections and joining communities in these chat rooms. So now I'll turn it back to you, Quincy.
Thank you, Valerie. And now we're going to have a fireside chat titled The AI Revolution, Why We Need Your Help. The chat will start with the presentation by Jeff Dean, who's a Google Senior Fellow and Senior Vice President for Google AI, to set the stage for the discussion. Jeff is a co-designer and co-implementer of Google's distributed computing infrastructure, including the MapReduce, Bigtable, and Spanner systems, the open source TensorFlow system for machine learning, and a variety of internal and external libraries and developer tools. He has many honors and recognition, including membership of the National Academy of Engineering, and now also keynote speaker at the Tapia conference. I'd now turn it over to Jeff for your presentation.
All right, so what I thought I would do to set the stage about our discussion is to talk to you about some of the potential for the use of machine learning, and in particular deep learning, to tackle a bunch of really important societal issues. And I'm going to be presenting the work of many different people at Google. So first, I think it's good to set the context by highlighting how much of an explosion of interest we are in terms of the field of machine learning and the ways in which it can affect lots of different other fields in the world. We're now on this exponential growth curve of research papers being produced in the field of machine learning. So this is a graph showing machine learning papers posted to arXiv, which is a research paper preprint hosting service, over time in the last decade or so. And we've had about a 45x increase in the number of papers per day being posted to arXiv. So this is just a phenomenal increase in interest. And a lot of the reason is because these approaches are now able to solve problems we didn't know how to solve any other way. And in particular, a technique called deep learning, which is really just a renaming of an older technique called artificial neural networks that has actually been around since the 70s and 80s, has really shown success on a variety of different problems. And the real interesting thing about neural network-based models is that they can take in very raw forms of input, things like the raw pixel values of images, and in a layered approach, learn to essentially predict interesting outputs from those inputs, given some training data. And this is really a pretty important property. So if you look at the kinds of things that we can train neural networks to do, you can take in the raw pixels of an image, as I said, and predict one of many different categories of what is in that image. So this is a leopard, or a car, or a truck, or a boat. You can take in audio waveforms and then produce as output a transcription of what is being said. How cold is it outside? And this is speech recognition. You can take in sentences in one language, hello, how are you, and produce sentences in another language, bonjour, comment allez-vous? That's language translation. And interestingly, you can even combine these modalities so that you can, for example, take in an image, and instead of just producing a category or something, you can actually have the model be trained to write a short sentence that describes that image, simply by training on lots of images and sentences that people have written that describe that image. And then you can take a new image and be able to get a reasonably good, high-quality sentence that describes that image. And the really great thing is, despite the differences in all of these different problems, the same underlying algorithms are generally able to tackle all of these different domains. And to give you a sense of the progress that has happened in the last few years, Stanford University every year runs something called the ImageNet Challenge, where you're, as a contestant, your machine learning system is given about 1 million images in 1,000 different categories. And the goal is to take new images and predict which of the 1,000 categories is represented by that image. And the winner in 2011 got 26% error. And we know from some human evaluation that humans get about a 5% error. This is actually not a totally trivial task, because in the 1,000 categories, there are 40 different kinds of dogs you have to know as a human in order to get them all right. And the progress over the last few years has been phenomenal. And so in 2016, the winning entrant got 3% error. So think about how revolutionary that can be. Essentially, we've gone from computers not being able to see to now computers can actually see and perceive the world on par with humans, or perhaps even slightly better for some kinds of tasks. And that's really amazing. So in the rest of the talk, I'm going to frame what I think the impact of these advances will be in terms of how it will let us tackle some of these grand challenges that we really, as society, need to be thinking about. And in 2008, the US National Academy of Engineering published a set of 14 grand engineering challenges for the 21st century. So problems that they felt were of the utmost importance for the entire scientific and engineering communities to come together and to really tackle. And the interesting thing is, I think machine learning is going to be at the core of helping us solve most of these problems. And in fact, within Google, we actually have work going on in all of the items listed in red. And I'm going to talk most about the ones listed in bold-faced red today. So one of them is restore and improve urban infrastructure. And the advances in computer vision are really on the cusp of enabling a really amazing technology, which is autonomous vehicles. For many, many years, people have dreamed of having cars that could drive you around by themselves and get you from place A to place B safely. And it's only in the last few years that computer vision has really gotten much better, and now enables us to build models of the world that take in the raw sensor data on the car. Things like lots of different camera viewpoints, the LiDAR, which is a spinning laser that gives you 3D depth information around the car, radar information, and to fuse it all together into a representation of the world around the car that looks like what you see in this video. And then to enable the system to plan and make decisions about what actions it's going to take in order to get you safely from A to B and to obey all the traffic laws and the signs that it's observing and so on. And this is really going to change how you think about urban infrastructure, right? If you had autonomous vehicles, you would summon a car to come get you on your phone. It would be just the right size car for you. It would be like a one-seater, or if you're at Home Depot and you've just picked up a bunch of lumber, it'd be a pickup truck autonomous vehicle. And I think this will really rethink how we think about building cities and urban infrastructure. Robotics is another really important area that is being improved dramatically through the use of vision. So in 2015, there was a task in robotics for how successfully a robotic arm could pick up an unseen object, an object it had never experienced before. And in 2015, the state of the art was about 65% success rate, which is not so great if you think about complex actions that might involve lots of different activities. If each of those sub-actions has about a 1/3 chance of failing, you're not going to be able to succeed very well. So in 2016, our robotics research group explored the idea of having lots of different robots in parallel experience the world and practice picking things up. And so essentially we got 10 robotic arms, put them in a room, and allowed them to practice picking things up. And they can tell if they succeeded or failed by whether the gripper kind of has an object in it, or whether it closed all the way and they failed to pick something up. Essentially that enabled a pretty big advance in the grasping success rate, from 65% up to 78%. And in 2018, with a bunch more algorithmic work and better data collection and so on, we're now able to get to a 96% grasping success rate. So this is something that now you can sort of fairly reliably depend on being able to pick up something that the robot is observing, even if it's never experienced it before. And this is all thanks to improvements in deep learning and computer vision and reinforcement learning algorithms. Advanced health informatics is another important area that I think will be impacted by machine learning. And I'll walk through one particular example in detail and then touch on a few other ones. So one of the hopes of machine learning is that we can use machine learning and AI to bring world-class specialist expertise to everyone at lower cost. You know, often world-class specialists are in a very limited number of locations, they have very limited time, and so they can only see a limited number of patients. But if we can use their expertise to train models that have quality of decision-making that is on par with the world-class specialists and bring that to everyone, that would be amazing. And so I'm going to use diabetic retinopathy as an example of how we might go about this in lots of different domains in medicine. So diabetic retinopathy is the fastest growing cause of preventable blindness in the world, and screening is what prevents blindness. So if you catch this disease in time, it's very treatable. But if you don't, then people will suffer full or partial vision loss before they're treated. And there's 400 million people at risk for this around the world, so this is not an insignificant problem. Essentially, if you have diabetes or you're at risk for diabetes, you really should be screened every year. And it's very specialized. Most doctors can't do it. You need some ophthalmology training in order to really do this. And in India, for example, there's a shortage of more than 100,000 eye doctors. And therefore, 45% of patients suffer full or partial vision loss before they're diagnosed. And it turns out, in the same way that a computer vision model can take in an image and tell you that's a leopard or a car, if instead you use roughly the same model and instead you train it on retinal images like the one you see on the left, and you get those retinal images labeled by ophthalmologists to the 5-point scale that you see on the right here that ophthalmologists use for grading retinal images for diabetic retinopathy, then you can train that model on lots and lots of retinal images and get the model to be able to predict for a new retinal image what is the grade for that image. And by doing so, you all of a sudden can have a model that is on par with board-certified ophthalmologists, or perhaps even slightly better. This is the F score that you see here. And this was work published in Journal of the American Medical Association. We'd like to do even better, though. And so there's a kind of specialist called a retinal specialist that has additional training in retinal disease. And they generally make better decisions than ophthalmologists who don't have this specialized training. And so if you get the images labeled by retinal specialists instead of ophthalmologists, but just board-certified ophthalmologists, and then train the model on that, you actually now have a model that is on par with retinal specialists rather than generalists. And this is kind of the gold standard of care, and this is what we would want for everyone in the world to be screened by, is a retinal specialist. And so now we have an algorithm that is sort of roughly the same quality as these retinal specialists. Explainability of these models is one thing that people often say it'd be really nice if they were more explainable, and neural networks have a reputation of being a bit of a black box. You feed in the input, you get the output, and you can't really tell why. Actually, over the last few years, there's been quite a lot of work on sort of making better tools to better understand how neural networks are making decisions. And I'll show you an example, like as an ophthalmologist, what ophthalmologists want to see when you say this retinal image is a 2 is why. And so if you see this and the model outputs moderate diabetic retinopathy, it's even more helpful if it can output some semblance of where it's looking in the retinal image that makes it think that this is a 2 as opposed to a 3 or a 1. And so there's a whole bunch of techniques that are being worked on in the research field to improve explainability of these kinds of models, and that's a really important area. And just a few other examples of how machine learning, I think, is going to dramatically improve healthcare. It can basically interpret CT scans to detect lung cancer. It can use the data in medical records using similar models to what we actually use for textual problems. You can view the medical record as like a long sentence about a patient, about all the different kinds of actions that have happened in the past to that patient, and predict the future parts of the sentence. and some work with machine learning and pathologists, where we actually showed that when you pair a pathologist with a machine learning model that is able to assist them in making pathology decisions, they actually are able to make decisions, make their diagnoses faster, but they also feel more confident in it because the model is able to highlight parts of the image that they should really be paying attention to. And a lot of the pathology problems that these pathologists are working on are really, looking in a giant sea of tissue for the tiniest little semblance of something that might be cancerous. And with a machine learning model that can help them guide to parts that might be interesting and pay attention to, they both make better decisions more quickly and feel more confident. So many advances depend on being able to understand text. And we've been doing a bunch of work in Google research on models that are better at understanding text. And so there have been some recent encouraging improvements. One of them is in 2017, a bunch of Google researchers published a paper called Attention is All You Need. This is the kind of commonly known as the transformer model. And the transformer model is a really important innovation because in most text models prior to this, essentially the model would process a token and would update its internal state. And then only after updating its internal state could it then go on to the next token, the next word, or the next sequence of characters. In the transformer model, the model is able to process a bunch of words in parallel and then use attention. So being able to look backwards at other parts of words that occurred before in order to make decisions. And it can do that in parallel, which makes it much more efficient to do computations on. And so that's what you see here, is many of the models above this line are these recurrent models that have to wait and have this sequential dependency. And so in this chart, we see quality of translation for English to German and English to French measured in blue score in the first two columns of numbers. And then the training cost in floating point operations. And what you see is that the transformer model was able to get the best performance on both of these language translation tasks using 10x to 100x less computation than the recurrent models. And so this was a pretty big leap forward. The next year, a different team of Google researchers used transformers. So everything in the blue circle here is kind of the core of a transformer model as the basis for a technique they called BERT, which stands for bidirectional encoder representations from transformers. And what they found with BERT is that the training technique they came up with is kind of cool and interesting. It may remind you of Mad Libs games if you ever played those as a kid. So the idea here is we want to be able to use context not just before the words, but also from after the words in order to be able to predict properties about text. So use these entire surrounding context. So we have a sentence or a paragraph here. And the way you train a BERT model is you drop some small number of words, 15% of them or so. And then you force the model to try to predict the missing words. So can it fill in the blank with the correct words? That's essentially the training objective. And a nice property about this is it's what's called a self-supervised learning algorithm, where essentially you can generate its own training data. So it's generating a little game for it to play in order to improve the training objective of the model, which is being able to predict these missing words well. And you can see that you essentially feed in the text, you drop 15% of it, you feed it through the model, and then you try to predict the missing words that I show there at the top. And this is really important because what that means is you can pre-train a model on this fill-in-the-blanks task with a large amount of self-supervised text. You just take text from around the world, web pages or books or whatever, and then you can fine-tune the model on a particular language task that you might care about. And this is shown to be incredibly effective for a wide variety of problems, especially where you don't have very many examples for the problem you actually care about. And so this is showing that BERT, for a whole bunch of different language tasks with different numbers of examples, ranging from 2,500 examples up to 392,000 examples, as you see in the upper part here, is able to outperform all the previous state-of-the-art approaches at the time it was published. And this has led to real advances in things like the production Google Translate system. This is for a whole bunch of different languages. So each, the x-axis here is different language numbers. Google Translate supports a little bit more than 100 languages, and so each one of these is a language, and the blue score of the different languages, sorted by the highest quality language. And what you see is when Google Translate launched, it was not using deep learning, and it was using a simpler statistical-based model that was able to get kind of okay quality for the best languages where we had the most training data, and then for about the 30th language, kind of pretty terrible quality, but still serviceable in a pinch. And what you see is the dramatic improvements in language translation quality for 105-ish languages that Google Translate supports. It's just been really remarkable, and that really brings the world closer together so that people can understand each other more effectively. Okay, finally, I'd like to touch on engineering the tools of scientific discovery. So one of the things, if machine learning is going to be really an important piece of what we're doing in solving many different scientific problems, we want good open source tools that everyone can use and contribute to and can use to solve different problems. And so TensorFlow is a system that we developed and released at the end of 2015 in order to help people solve machine learning problems using the same tools that we've been using. And one of the nice things about this is we hope the community would develop and would all come together and work on improving the tools together. And that is indeed what has happened. When we first released TensorFlow on GitHub, which is a popular open source hosting facility, it had quite a bit of interest, and then that interest has continued to grow. This is an interest measured in GitHub stars, which is the number of people kind of paying attention to that repository for TensorFlow compared to a bunch of other open source machine learning libraries. And it's had quite a lot of contributors. So roughly a third of those contributors are people within Google employees, and the rest are other people in different universities or companies or individuals. It's been downloaded 130 million times. And so we've built up a pretty vibrant community, and we're pretty excited about all the different things that people are doing with TensorFlow. And I'll just highlight a couple. So there's a company in the Netherlands that is building fitness sensors for cows, and they analyze the sensor data using a machine learning model that they implement in TensorFlow. There's a collaboration between Penn State and the International Institute of Tropical Agriculture in Tanzania that is building machine learning-based models that run on device, on the phone, without any network connectivity, for doing cassava disease detection. So in the same way we can have machine learning models for human health problems, we can also have them for plant health problems. And this model enables you to take a picture of a leaf and diagnose what the problem of the plant might be and suggest, maybe you need to give it a different kind of fertilizer or whatever the remedy might be. And this is an example where machine learning wants to run in lots of different environments. It wants to run in large data centers. It wants to run on GPU cards in your desktop, but it also wants to run without a network connection in the middle of a cassava field on a relatively low-powered cell phone. And so being able to run TensorFlow models in those environments is really important. And the other thing I'll point out is that deep learning is really transforming how we think about designing computers. And that deep learning has two really nice properties in terms of computational behavior. So the first is that all the algorithms I've described are fine with reduced precision. So if you do those calculations to 1 or 2 decimal digits of precision, that's fine. You don't need 6 or 7. And that's really helpful. If you think about yourself multiplying those numbers, it's a lot easier to do the problem on the left versus the problem on the right. And they're all made up of a handful of specific operations and different compositions of these operations. So essentially linear algebra operations, things like matrix multiplies, vector dot products, these are all kind of at the core of deep learning algorithms. And so if you can build computers that are specialized for reduced precision linear algebra, essentially you have built a computer that is ideally suited for deep learning training and inference, and you don't have to worry about lots of other kinds of computations that traditional CPUs have developed techniques for over the past many decades to make run efficiently. Instead, we want to make this kind of computation run efficiently. And so that's what we've been doing. We've been building things called tensor processing units, TPUs. And if you look at a TPU board, this is 4 chips. And if you look at one of the chips and we look inside, one of the beauties of the fact that we want to run these very specialized computations is that the actual computer chip is quite simple. It's essentially a big matrix multiply unit and some scalar and vector units for things that are not matrix multiplies, and some high bandwidth memory and connections to that to feed the matrix multiply units. And that's pretty much it. So that's a really much simpler design than a traditional CPU, which has things like branch predictors and TLBs and L1 caches and L2 caches and all these kinds of things. And we've been, producing different generations of these. The 3rd generation is like the 2nd, except it runs faster and adds water cooling. So there's actual water in those pipes, bringing water to the surface of the chips, which is exciting. And they're designed to be connected together into larger configurations that we call pods. And really, this enables us to scale machine learning models to larger data sets to get more accurate results, but also enables us to more rapidly try out machine learning research ideas. So if you can try out a machine learning research idea in 5 minutes or 10 minutes instead of a day or a week, that dramatically changes your productivity as a researcher. It just forces you to think very differently about what ideas you might want to try. And I'll also point out that we have work going on at the very other end of the power spectrum, where you want things that might run very efficiently in things like a cell phone or a battery-powered camera or other things like that. Okay, a vision for where we could go. What do we want? I think we want really large models that are sparsely activated. And we want a single model to solve many tasks. Today in machine learning, many of the models we work with tend to be very specialized to one thing or a handful of things, and not all the different things we want a model to do. And we want to dynamically learn and grow pathways through this large model for new tasks. And we want the model architectures to adapt as needed. And adding a new task can leverage the existing things we already know how to do and representations. So I have a kind of cartoonish diagram of how I think machine learning models in the future might look, or machine learning model to solve many things. So here we have a model with lots of different pieces, and it's made up of components, which are pieces of these machine learning models with state and operations. And it's already figured out how to solve some of these tasks using a set of components, and now a new task comes along. And we'd like to be able to do some searches over one of the other components in this model that might help us get into a good state for this new task. And so maybe we do a search and we find that this sort of flow through the different components works pretty well for this new purple task. And maybe we care a lot about this task, so we want to add a new component and have that component be used for the task to improve its accuracy. And that new component can now be used for solving new tasks. And maybe that component itself is learning through some sort of search process what architecture, what the model structure is going to be most effective for solving that particular problem. And finally, I'll touch on thoughtful use of AI in society. One of the things we've done at Google is thought quite a lot about how we want to use machine learning, and we've come up with a set of principles by which, when we're thinking about using machine learning for a particular task, we make sure that it is in accordance with these principles. And I'll point out that many of these areas are actually active areas of research, and so we want to apply the best known techniques for example, avoiding creating or reinforcing unfair bias in the models, but we also want to continue to do research into even better ways to avoiding those things. And so we have quite a large number of people in our research organization that are focused on ethical AI, and these are just some of the areas they focus on. Defining algorithmic and cultural approaches for diversity and inclusion, making sure that everyone is included in the AI models that we think about deploying, and that they're treated fairly in an unbiased manner. Ethical practices and how we gather data and use it in different machine learning problems, and responsible democratization to share these ideas. And I'll just highlight that there's quite a lot of research papers in this place. I'll just highlight one here, which is model cards for model reporting. One of the things that is really important in a machine learning model is to highlight how that model has been evaluated for seeing if it has different kinds of bias. And the model card is a sort of think of it as a nutrition card for machine learning models, where you can learn at a glance what the developers of the model have done, how they've tested it, how they've tried to ensure that it is unbiased in certain kinds of ways. And at Google, we're deeply committed to racial equity. One of the things that we believe in is we need to make our own workplace equitable, and so we're working to increase the underrepresented employment of underrepresented groups in all of our workforce. We try to have products that improve many different kinds of communities all around the world. We are deeply committed to STEM education, both at K-12 level and undergraduate and graduate level. And we've been supporting racial justice organizations, and you can learn more about that here in our commitments to racial equity. And so with that, I think the message I'd like you to take away is that AI is really helping advance many fields simultaneously, and we need your help. We want everyone who's interested to be participating in how do we train these machine learning models to improve the world and make it equitable for everyone. So with that, thank you very much. And I'm going to stop my screen share and turn it over to Charles.
All right, thank you, Jeff. And so I want to introduce our moderator for this panel, Charles Isbell, Dean of College of Computing at Georgia Tech. We also have joining Jeff as panelist is Beata Shahriari, Executive Director and Distinguished Engineer, JP Morgan Chase. We have Navdeep Jaitly, Senior Member of Machine Learning Ventures, DE Shaw Group, and Anya Shivnan, Vice President for Program Management and Qualcomm Research.
Just let me take a moment to say I'm honored to kick off the Tapia opening with this fireside chat on AI. I think both Jeff's talk and this general topic are very timely and in line with the theme of the conference, which is that inclusion drives innovation. So here's quickly for everyone to know, here's the panel's going to go. The key thing you have to know is that we have to end at 1:15, which is about 25 minutes from now, to give everybody time to move to the next session. But you should also know that some of the panelists will be available afterwards, so there'll be plenty of time for you to follow up with them, talk and ask questions. Speaking of questions, if you have any, please use the question and answer button tab pull down on your Zoom screen or wherever you are, and put questions there. Valerie Taylor will be looking for some questions, and hopefully there'll be enough time to take one or two of them. But I'm going to start off with a question. I have actually two questions I want to ask the panelists. And then we'll open up for some questions, and then I'll wrap it up and turn it back over to Quincy. So for everyone else who's not Jeff on the panel, I think if you were paying a lot of attention, you'll notice that implicit in Jeff's talk is a series of statements about what the cool, hard, and important problems are for AI machine learning, particularly and especially as Google sees them. So my question for each of you is about AI in your own industries and sectors. So what does it look like now? How's it being used? And in particular, I'm curious, what do you see in your own worlds that are similar to what Jeff has outlined? And what do you see that is different? Navdeep, why don't we start with you? And please, you should feel free to tell us a little bit about yourself as you answer the question, but do it all in about 3 or 4 minutes. And then Navdeep, after you're done, Beata, and then Anya, why don't you answer the question?
Okay, great. Thanks, Charles. Firstly, thank you everyone for the organizers for giving me a chance to present some of my work in AI in the conference today. I'm really excited to be here, and I hope I can influence some of the audience that there's a lot of exciting work to be done in this area. I think Jeff has done a fantastic job of doing that. So thank you, Jeff. So I work now in the field of quantitative finance. In my past life, I worked in computational biology and even at Google Brain in Jeff's team looking at different areas. So what's interesting about all of these areas is that the definition of AI is slightly different from one group to another. So when I talk to my past collaborators and colleagues in computational biology, AI means one thing, and when I talk to people in more of the tech space, in the cutting edge tech space, it means something else. So in all generality, of course, AI is about intelligence, but in practical implementation, it varies from industry to industry. So if you consider AI as, which is a fairly safe definition for most industries, as the application of statistical models with decision-making using statistical models, then communities like quantitative finance area, which I work in, have been using AI for a very long time. What's changed over the last few years is that the way decision-making is done and the way the individual models, the statistical models are built, have evolved with the establishment of such phenomenal models that come out from deep learning these days. It's fair to say that people had AI in quantitative systems several years ago, but if you had told people 10 years ago that they should use neural networks to model prices of instruments, I think a lot of people would have lost sleep. What has changed over the last many years is that AI techniques have become a lot more robust. There's been a lot of demonstration of their use, and so people have been applying them to different areas, even in areas such as finance. Now, what's different about applying it to areas such as finance is that the amount of statistical rigor that goes into building these models is very intense. So it's not uncommon for people to spend more time looking at the model results than spending time building models. So you'll have a team that develops models, and then other people will, like the team itself, will look at their results for a long time and then pass it on to specialists who just understand what the models do or the data looks like, and they'll pass it through various more stages. So I think there's this evolution now in the trading systems where everything is becoming automated. For the younger people in the audience, there was a time where traders used to be in a pit yelling across the room, trying to get the attention of other traders to buy or sell their instruments. And now, of course, the whole thing is automated with servers from trading markets being on the floor, and then companies trying to put their automated servers right next to these servers to try and get their transactions executed very fast. So with this evolution of automation, the industry has become a lot more reliant on automated technologies, and also the finance world, the sheer volume of financial transactions has gone up so much that it is unavoidable to use AI. What's interesting going forward is to see how these systems of these more intelligent algorithms can be put into these systems, because it's really hard to know how these algorithms will interact with each other when they're out there everywhere, each acting on their own. And so a lot of exciting work in the future, I think, will be about figuring out how these algorithms work and like how do you keep them stable in various systems.
Thank you. Beata?
Hey, so my name is Beata. I had applied AI for global technology infrastructure at JPMorgan Chase. So I'll talk a little bit more about, I guess, the back office part. Technology is really vital to the performance of the financial sector, and JP is the biggest bank in America, actually one of the top 10 in the world. And to paraphrase our CEO, Jamie Dimon, it's absolutely essential that we be up and functioning for all of our customers each and every day. How else would we process $6 trillion in payments or buy and sell $2 trillion in securities and foreign exchange transactions for our clients on a daily basis? Even our combined credit card and debit card transaction volume totals $1.1 trillion a year. And so the importance of technology is similarly evident in our tech spend, which is $11 billion. Improving the performance of our infrastructure benefits our customers, it improves our efficiency, and it ultimately affects the bottom line. But why specifically use AI to drive infrastructure optimization? So tech infrastructure is actually really optimal for AI transformation. AI is one of the most effective and efficient ways of driving optimization in our business, especially in operations and infrastructure management. Benefits are easy to measure since performance is already monitored closely, and it's one of those areas where benefits will be most widely felt. So I'll give you an example in our space. Anomaly detection on our networks, where we've successfully been implementing deep learning to really move the needle for the business. So based on what I just said, you can imagine the expansiveness of our network surrounding the globe. And network health is a critical part of being up and functioning. They allow information to travel between all of our assets. And conversely, network issues can cause significant impacts to our business and clients. There's tens of thousands of network devices routing over 1 trillion events daily. And while we have incredible resiliency and rerouting capabilities when issues do occur, there are a lot of silent lurkers that cause what we call gray failures. Now, these have various causes, but the important thing to note is that these causes evolve and change over time. And they're even sometimes undetectable to the vendors providing the devices themselves. And similarly, monitoring can quickly turn into a noisy nightmare. So we've employed deep learning techniques, such as autoencoders, to successfully detect the previously undetectable in a matter of just minutes. And this allows the network teams to triangulate and resolve issues prior to any business impact. Similarly, it's allowed us to also work better with the vendors directly, and that way we can detect silently defective and really expensive devices that need to be replaced. Going a little bit more into specifics, we use concepts like feature families and AI solution architectures so that we can deploy these solutions to thousands of new devices in just hours and only with a couple of lines of code. And this means that we're also improving our ability to capitalize on AI while lowering the burden of tech debt to perform AI. That means faster deployments, fewer models to maintain, and easier scalability. Right, the ability to learn is really powerful. The solutions evolve and even improve with time, and so the optimization actually becomes continuous with minimal human intervention. Now, with regards to infrastructure management, the growth of the cloud, containerization, and serverless architectures come at a cost of significant infrastructure management burdens. And as adoption of these technologies increase, so has the complexity. An application may require tens of different services, each running on their own container. And AI can spot surges in demand far faster than any human, meaning you can use AI to handle resource allocation, spinning up new instances as required. And as soon as demand drops, it can reallocate resources, which saves money. Similarly, it can learn demand patterns, and most applications see layered temporal cadences in demand, too complex for humans to analyze reliably. And so machine learning can be trained to spot these patterns with a high degree of reliability. And this allows the system to preempt any expected spikes in demand. So you can see AI has kind of become a critical capability for modernization of technology infrastructure. Now, if you still feel like solving infrastructure problems isn't necessarily sexy, they're actually quite significant in scale and complexity, but solving them is really game-changing. I'd be remiss not to mention MapReduce here, a great example that was absolutely paradigm shifting. And thanks to Jeff solving this critical infrastructure problem, we've seen some of the greatest evolution in how people fundamentally think about how to perform advanced large-scale analytics. So to wrap it up, tech infrastructure is critical for the global economy. Solutions to infrastructure problems have shown to drive widely applicable advancements, and tech infrastructure is really primed for AI transformation.
Thank you for that. Anya?
Good morning, everyone. Let me start. Yes. I've been at Qualcomm for the past decade, which is almost equal to the same amount of time that Qualcomm have been doing some AI research. And for those of you not familiar with Qualcomm, we focus on technologies, that transform how the world connects, computes and communicates. We've pioneered 5G, and that's leading to connected vehicles, massive downloads, and split-second machine-to-machine communication. But with respect to AI, we're leveraging the scale and the power efficiency of the mobile platform and making AI ubiquitous by focusing on power efficient and performance optimized solutions. For example, AI in smartphones is offering enhanced experiences and new capabilities, such as on-device natural user interfaces, for voice and always-on sensors, where you have the ability to do that AI work, close to the event, and then engaging the cloud and for the much more complex types of workloads. Superior photography. So, for many years, we have image sensors tensor processors that are very complicated. But now with the addition of AI, there's an ability to add smart low light adjustments to your photographs, smart filters across a complex image, highlighting water, sun, or sky and skin in an appropriate way to actually enhance the camera and the image without ever having to upload and apply your own filters. So at Qualcomm, we have a heritage of working in a compute and power restricted and constricted environment. And we feel from an AI perspective that intelligence per watt will become an AI benchmark. We also feel like mobile is a pervasive AI platform, with smartphone shipments, projected to be in the over 8 billion between now and 2024. So one of the comments Jeff made was about democratizing AI, and we think that is something that the smartphone platform and with 5G and the Internet of Things, that's another way to do that and bring it to new frontiers, form factors, and adjacent industries. We're seeing it in virtual reality, even in artificial reality, where we're able to aid accessibility and information to all different sectors of the community, with the focus for many companies, and even what Jeff mentioned there with smart automotive applications. Just providing even intelligent in-vehicle experiences is a step toward that. And of course, infrastructure and edge cloud, bringing more inference power to the edge of the cloud is also a big focus for us. So what we're doing is we're on our 5th generation of an AI engine, and we comprise hardware and software components. We're focused on device acceleration of AI and smart reduction of the size of these massive networks so that they can work effectively on device close to the data, which gives us opportunities to increase privacy and offer additional security options to consumers.
So thank you very much for that. It's actually all actually incredibly interesting. So we're going to take at least 2 questions from the audience, and I know what one of them is, as I was sort of looking through the questions and answers. So let me see if I can reword it. So one of the things, Jeff, that you mentioned in your talk was ethics, and a lot of things surrounding that, and a couple of the other panelists have brought this up as well, and there's at least one question from the audience about this. But I was struck by another phrase that you used in your talk, which was around Google's efforts in, and I think I'm quoting this right, engineering tools for scientific discovery. So all the stuff that you talked about is truly amazing. It's had a pretty big impact out in the world. But another way of thinking about it is that that's a lot of power to put out there, right? So one of the common questions that keeps coming up whenever we talk about ethics and we talk about the implications of machine learning and AI running free in the wild is that it can be used for truly impactful ways, but those impacts can also be potentially dangerous, such as determining whether someone should be granted parole, or generating images from low-dimensional images of random AI researchers and turning them all into white people, just to pick a random example recently that went around on Twitter. So if we don't think about it specifically in terms of ethics, but we think a little bit more broadly in terms of responsibility. So Jeff, this is for you first, and then I would welcome any comments from the panel. What do you think are the key issues for developing computing in general and AI in particular responsibly, and how does it tie in with the principles that you mentioned with Google?
Yeah, I mean, I think you have a really good point that a lot of sort of very low-level machine learning tools like TensorFlow can obviously be used in a whole variety of ways. It's sort of like an operating system. You could run terrible things on the operating system, or you could run great things. And then the closer you get to a real-world application, the more I think the responsibility is to look carefully at how that application is being used. And I think, obviously there are a lot of applications that I would not want to build. One of the things I didn't show in our AI principles is we've actually outlined a handful of areas where we will never work. In particular, like working on autonomous weapons is one of them that I think, Google as a company has taken a stance there that we draw the line. And, another one is facial recognition. I think, in our own products, facial recognition can be useful. Like we can help cluster photos in Google Photos of like, this is all the pictures of daughter number one, and so on. But on the other hand, it has all kinds of dangerous implications in surveillance-related applications that we would not want built. And so one of the things we've done is for example, our cloud APIs, we have a set of ML APIs for computer vision and for speech recognition and so on. And we've chosen not to build a facial recognition general purpose API because we think the potential for misuse there is actually quite large. Like once you release a general API, you kind of lose control over how it's used. And so that's kind of the thinking. We have a fairly robust review process of looking at potential uses of AI and machine learning in our own products and in things we release as cloud APIs, for example, where we sort of look carefully at that use and compare it with, is it compatible with our principles? And facial recognition is an area where we've made a decision not to have a general API as one concrete example.
Excellent, thank you for that. So any other panelists want to jump in? I guess I'll give you each a chance because it's difficult for people to talk over one another. Why don't we start with you, Anya? Is there anything you want to add to that or any thoughts you have about responsible AI?
Yes, certainly. We also view AI as a net positive humanity and transforming industries like healthcare. And, sadly, just like any technology, it can be used and or trained for good or bad. So we certainly want to make sure that it's monitored and improved when we can, and that can be in either new architectures. And for us, when we're looking at large models and we're quantizing or compressing for them to work with the same accuracy in a constrained environment, are we compressing and quantizing appropriately? Is the accuracy that it's being tested against appropriate? And so ensuring that we follow and not lose something as we make those transitions is important for us. Another area where we feel we can maybe offer some opportunities is in privacy. And so, so many people are using phones as their main connectivity to the rest of the cloud. And what can we do to offer our customers to enable privacy? And when data is, used or stored, what's the choices that you can provide to consumers to make decisions about what's shared or not? So we look at ways to research into those areas and see what we can develop and offer as tools to our customers and implementing in the platform.
Excellent. So Beata and Navdeep, before you answer, Valerie just texted me the question that she was taking from the audience. So rather than have her say it, in the interest of time, I'm just going to kind of summarize it. It ties in with this question. It's about bias and how you reduce bias in machine learning and in AI. Very similar to this sort of question around responsibility. So I wonder if either of you could, and Beata, I'll start with you, if either of you can sort of speak to that question about that particular aspect of responsibility. And I'm curious whether any of you think that maybe the mechanism for that has to do with the kinds of people who are actually doing that AI and machine learning, and what you may or may not be doing in your own companies, in your own world, to make certain that, I don't know, you create the kind of environment where different people can see problems differently as a result. So Beata, take it away.
Yeah, so a couple of things, right? I think diversity in our AI workforce is pertinent for reducing unintended bias in AI solutions. But university pedigree is one of the largest factors in screening for our workforce. And this practice disproportionately takes out Black and Latinx people from a system known to already disenfranchise students. The lack of diversity in tech workplaces, I believe, is a result of all the ways our institutions keep people of color from economic opportunity. And the disadvantage of some people comes at a cost to all of us, right? It's tragic for both them and all of us who missed out on their work that could have enriched our lives, given us a better understanding of the world, and gotten us closer to solutions of problems that we all share. I think as technology leaders, we got to do our part to really create enabling circumstances. For us, our aim is to help create equitable opportunities and democratization of work to address this. By lowering barriers to acquiring and applying these valuable skills, I think we can drive advancements for both our firms and the communities that they serve. right? So employees should be representing customers. And in order to build products that serve all customers, a critical mass of the employees who actually represent the many identities of customers is needed, because there's no shortcut to really understanding what customers experience. The second thing is that infrastructure has become, I believe the concern is that it's going to become, or it already has become, a gatekeeper, since we're the most fiscally inaccessible. So, you know, the threshold to fund and host infrastructure capable of deep learning is high, and thus it's kind of limited to those who can afford it. So what does that mean? You're going to see a rapidly growing divide in progress in different sectors and communities based on their access to capital. So as an example, AI work that could benefit public housing challenges would remain largely underexplored or underfunded with respect to AI work that could benefit trading strategies. And this is kind of due to the ability of each sector to invest in the ideation, realization, and technological requirements of these advancements. And last but not least, AI ethics. There's a bit of irony that we're starting to see, where the actual groups that are really well-intentioned to be focused on AI ethics are themselves lacking some of the diversity needed and diversity of thought needed. So we have a little bit of a chicken and egg situation. And unfortunately, although, and I can't remember who to attribute this quote to, although talent is equally distributed, opportunity is not.
Love it. Navdeep.
So my view on this is mirrors a little bit of what Jeff said about the role of personal responsibility. I think deep learning by itself is a tool, and you know, this tool is remarkably powerful. You give it data and it munches up all kinds of patterns, and you know, reproduces things that are in there that you know of and things that you never even thought to look for. So I think as practitioners, one of the very important goals is to make sure that we spend a lot of time looking not just you know, at like summary statistics of how good did the model perform, but actually digging deep into the data and its implications, because really there's a lot of hidden surprises there. And so the context of the machine learning algorithm is the people that apply it. So it is, you know, my opinion that if we want to sort of apply these technologies responsibly, we have to do it within the context of groups that are, you know, represent diverse viewpoints, represent different concerns. And so it's really important to drive, you know, the communities that develop these technologies to look and use these technologies to look more like the rest of the world. And so I think, you know, tech has in the past been lagging in this approach, but we've been making some great progress, and have, you know, really been excited to see where this is going. At DShaw specifically, we're, you know, looking at working on more of the hiring on the funnels, and so we want to encourage people from underrepresented groups to, you know, come and look at finance and bring their viewpoints and their skills to the area. So we have a bunch of initiatives, and it's been very interesting to see the growth of the intern pool over time. But I think, you know, it's still, you know, work in progress. You know, very, to me, like the most important bit of information is that, you know, it's not just the models, but who is looking at the models and how we bring our concerns to their application.
Great. So, and based on all the notes in the chat, I think everyone's appreciated all of your answers. So we're about out of time. I've been given 2 additional minutes, so I'm going to ask you a very, very difficult question, and each of you has 20 seconds to answer it. Here's the question. What is the key technical challenge that you're trying to deal with in your own world? What is the idea that's missing and that you need help with? Let us know let the audience know what we should be thinking about. Again, you have 20 seconds to answer this, and we'll do it in this order: Jeff, Anya, Navdeep, and then Beata. 20 seconds, Jeff, go.
Sure. So I think one of the key things that I'm personally working on with a group of people is how do we train a single model that can do 1 million tasks? Right now, we tend to train separate machine learning models for different things. And that means every problem we start with, we forget everything we knew, and we try to learn from scratch how to solve that task. It's sort of like forgetting your entire education every time you try to do something new. That seems crazy to me.
So our team is starting to really think about distributed ML when we think about our distributed and a highly scaled mobile platform. How can we leverage that, maintain privacy, and you know, federated learning is essentially what we're talking about, and that's our one of our next big challenges. and on-device learning.
The biggest thing that I'm concerned about is looking into the internals of these models and see how they influence the predictions they're making, and also how a bunch of independent agents out there might influence each other unknowingly.
So I'll expand a little bit on what Jeff said, right? I think access to low cost, low energy, which translates into low carbon emission, producing compute is really critical to reach what he's describing as, artificial general intelligence, right? We need to increase in computational power exponentially in order to be able to increase the computations per second. I think if we want to get to, marrying human performance where you can apply the same learnings to different areas, you need to be capable of approximately an exaflop. And today, I think the record is like 33.86 petaflops.
Excellent. So I'd like to thank each and every one of you. As is always the case, we are running out of time. I see there's lots of questions. Quincy, let me turn it over to you. And thank you, everyone.
Yes, thank you. Let's give them all a round of applause. All right. Snip snaps. I would get up and dance and cue some music, but I'm not. All right. Enjoy the rest of the day.